Deep within the vast and mysterious constellation of Leo, a world 120 light-years from Earth has quietly whispered a secret that could change the future of humanity. For years, scientists have dreamt of such a discovery, but now, thanks to the James Webb Space Telescope, those dreams have become a reality. It wasn't just a fleeting hope or a distant fantasy. It was a message, a chemical signature, dimethyl sulfide, unmistakably a mark of life, emerged from the vast darkness of space, sent across the cosmic expanse by an alien world named K2-18b. This molecule, this faint trace of life, was not merely a curiosity. It was an undeniable signal that something was living on that distant planet, something capable of creating and maintaining a chemistry so vibrant, so unpredictable, that it could not have formed in a lifeless environment. The discovery was so significant, so staggering, that scientists were left speechless, struggling to comprehend the magnitude of what they had just uncovered. The signal wasn't a faint, wavering possibility. It was as clear as a beacon in the dark, with a 99.7% certainty that life existed on K2-18b. For a moment, time seemed to stand still at Cambridge University, where astrophysicist Niku Medusan stared at the screen in awe. The numbers and patterns on his monitor danced like the remnants of some ancient interstellar symphony, a song that had traveled more than a century across the cosmos, echoing the pulse of an alien world. And then, the realization hit. This wasn't just a discovery. This was evidence. Concrete proof that life was not an anomaly, not a fluke of chemistry, but a principle that governed the cosmos. If life could exist on K2-18b, a world orbiting a small red dwarf star, what did that mean for the rest of the universe? What did it mean for humanity, who had long searched for signs of life beyond Earth? In the vast emptiness of space, amidst the unyielding cold and silence, life was speaking, and it was speaking loudly. As Medusan processed the data, his hands trembled, not from the cold of the lab, but from the magnitude of the revelation. His mind raced with possibilities, as though the very fabric of reality had shifted beneath him. If you're interested in diving deeper into this groundbreaking discovery and being part of the search for more answers from the stars, don't forget to like the video and subscribe to the channel. Your support helps the channel grow, and it's completely optional, but it makes a huge difference. The planet, K2-18b, had been hiding its secrets for eons, and now, finally, the curtain was pulled back, revealing a world that defied expectations. The planet's dense atmosphere, a thick protective blanket of hydrogen, methane, and carbon dioxide, wasn't a barrier to life, but a cradle for it. Instead of roasting under the heat of a red dwarf star or freezing under its dim glow, K2-18b remained a perfect balance, with temperatures hovering at a constant 49 degrees C, 120 degrees Gan. While this might seem inhospitable to us, this delicate equilibrium created an environment where water could exist without boiling away or freezing into solid ice. The star around which K2-18b orbited was a small, quiet red dwarf, nothing like the blazing ball of fire that is our sun. Red dwarfs, as astronomers had long suspected, were not ideal candidates for hosting life. Their weak light and close proximity to their planets had been thought to lead to unstable climates, and yet, here it was, a planet thriving in the warmth of its star's eternal glow. Medusan's team, working tirelessly in the weeks that followed, gathered more and more data. They studied the planet's atmosphere, which was not just stable, but in constant living flux. Methane, carbon dioxide, water vapor, these were the building blocks of life on Earth, and they were abundant on K2-18b, but they weren't in perfect balance. Instead, they fluctuated in a way that could only be attributed to living organisms, an active, breathing biosphere that was reshaping its environment to maintain life. As the days passed and the data piled up, the team realized they were no longer dealing with a mere anomaly in the vastness of space. They were witnessing the echo of an ancient world, one that had lived and breathed for far longer than humanity had even understood the concept of life beyond our world. A planet that had never stopped evolving, never stopped adapting, as its slow, steady dance around its red dwarf star continued. Yet, there was something even more profound about this discovery. This wasn't a young, budding planet that had only just begun its journey toward creating life. K208b was a world that had already been living for billions of years under the steady glow of its star. Its atmosphere, rich in gases, fluctuating like the breath of a living creature, was a testament to the slow, patient evolution of life. In the long, calm rhythm of its star's eternal life, K218b had found balance, not through sudden bursts of fire or impact, but through slow, methodical growth. The implications of this discovery went far beyond the realm of science. It touched the very heart of humanity's understanding of existence. For centuries, humans had looked to the stars with a sense of loneliness, convinced that life was rare, an anomaly that had sprung forth from a perfect set of circumstances. But now, the search for life had taken a radical turn. Life was not an accident, it was a process, a cosmic rhythm that repeated itself across the stars, patiently waiting for the right conditions to emerge. And those conditions were not limited to Earth-like planets around yellow stars. They could occur around red dwarfs in the shadow of cool, patient suns that had been burning for trillions of years. As the team at Cambridge celebrated their unprecedented discovery, they were acutely aware of the significance of their findings. What they had just uncovered was not just the possibility of life elsewhere. They had found proof that life could exist and thrive in environments radically different from our own. The discovery of K218b had reverberated through the scientific community, sparking an uncontainable excitement. The certainty of life existing on an exoplanet was not just an academic milestone, it was a profound shift in humanity's understanding of existence. For years, we had searched for Earth-like planets around sun-like stars, assuming that life could only thrive in conditions that closely mirrored our own. But now, a new definition of habitable had emerged, one that shattered old paradigms and opened up a universe of possibilities. As the data continued to flow in from the James Webb Space Telescope, Meduson's team began to piece together a more complete picture of K218b. The planet's atmosphere, once thought to be a simple mixture of gases, revealed an intricate living system. The chemical imbalances that had first caught their attention were now seen as part of a larger, dynamic process. These fluctuations, gases that didn't settle into equilibrium, were the signature of life itself. The team began to refer to it as chemical disequilibrium, a term that described the constant movement and reshaping of the planet's environment. On lifeless worlds, such disequilibrium would stabilize quickly. But on K208b, it persisted, a testament to the planet's active living metabolism. This was no sterile world. It was alive, breathing, evolving under the watchful gaze of its red dwarf star. The more the team analyzed, the more evidence of life they uncovered. Methane, carbon dioxide, water vapor. These were the gases of life, found in the upper atmosphere in precise fluctuating patterns. In the absence of ammonia, a toxic byproduct that would typically accumulate on a lifeless planet, the scientists were faced with the unmistakable conclusion: life was actively cycling, using gases and processes to sustain itself. But what kind of life was it? And how did it function? In the weeks that followed, the questions deepened. Meduson's team had only scratched the surface. The planet's immense hydrogen atmosphere, which acted as a kind of heat trap, revealed a constant, stable temperature, a perfect environment for liquid water to exist in a state of perpetual flow. Water, life's most essential ingredient, was abundant and stable. But unlike the seas of Earth, these oceans were strange, deeper than any earthly sea, hidden beneath layers of dense, shimmering gases. From orbit, K218b appeared as a glowing marble in the dim light of its red sun. The vast oceans, stretching for miles and miles beneath the mist, blurred the line between sea and sky. Water vapor and clouds merged into an ethereal haze, creating an environment where the boundaries of air and liquid were almost indistinguishable. This was no mere atmosphere. It was a living, breathing entity, constantly shifting, constantly changing. But how? The answer came when they began to analyze the deeper layers of the atmosphere. Webb's instruments, designed to read light from the distant planet, allowed the team to decipher the atmospheric composition in unprecedented detail. And what they found was more than just chemistry. It was biology in motion. The researchers could see, from the fluctuating levels of gases and the intricate chemical patterns, that life on K218b was not a single isolated phenomenon. It was an ecosystem, possibly teeming with microbial life, with complex webs of energy cycling through the atmosphere, feeding and sustaining one another in a balance that had been maintained for billions of years. Evolution on K218b had no need to rush. Time itself was on the planet's side. The red dwarf star, small and steady, had given the planet a steady hand, an eternal patience that allowed life to unfold at its own pace without the cataclysmic disruptions that had shaped life on Earth. The team's excitement only grew as they realized the profound implications of their discovery. If life could thrive under these conditions, on a planet with a hydrogen-dominated atmosphere orbiting a red dwarf star, then what other forms of life could exist out there in the galaxy? The answer was dizzying. Life, in its myriad forms, could be everywhere. It wasn't just possible, it was inevitable. The news spread like wildfire, capturing the imagination of not just the scientific community, but of people around the world. The implications of K218b's discovery reached far beyond the confines of astronomy and chemistry. For the first time, humanity was not just asking whether life existed elsewhere in the universe. We were certain it did. And K288b was just the beginning. As the weeks passed, new data continued to stream in from the telescope. Every observation brought fresh insights into the planet's ecosystem, and with it, new questions. But amidst the excitement, a realization began to form in Medusan's mind. While their work had just begun, they were already standing at the edge of something monumental, a future where humanity could no longer see itself as isolated in the universe. Life, in its countless forms, was no longer an anomaly. It was a fundamental part of the cosmos. Medusan began to see the discovery of K218b as something far more profound than just a scientific breakthrough. It was a message. The universe, it seemed, had been alive for eons, its vast oceans, dense atmospheres, and quiet red dwarf stars all playing their part in an eternal dance of life and balance. K218b was not just a planet. It was a mirror, reflecting the enduring persistence of life itself, a life that stretched across the stars, waiting to be discovered. But the mystery wasn't over yet. If life on K218b was so abundant, so intricately woven into the fabric of the planet's atmosphere, what did that mean for our own world? Were we just another cog in the wheel of cosmic life? Were the atoms in our bodies, those same atoms forged in the cores of long-dead stars, part of a greater universal pattern? Could we too find our place in this vast living network of worlds? To answer these questions, the team would need to go further, to peer deeper into the heart of K218b's oceans and atmosphere, to understand the full extent of its biology and evolution. They were no longer just studying a distant planet, they were unlocking the secrets of life itself, one chemical signature at a time. And as the team continued their work, Medusan could feel the weight of history pressing down on him. This was the beginning of a new era, one where the search for life was no longer a distant dream, but a reality. And with each passing day, the universe was whispering more, its secrets unfolding like pages of a long-lost book. As Medusan and his team continued their research, the discovery of life on K218b started to ripple through the scientific community and the world at large. What had once been a speculative fantasy had now become an undeniable reality. The implications of the discovery went far beyond the immediate scope of astronomy or biology. It was a catalyst, reshaping our understanding of the universe, life, and humanity's place within it. Across the globe, from research labs in Cambridge to the quiet halls of the United Nations, experts from all disciplines began to realize that what had once been confined to the realm of science fiction was now a pressing reality. The whispers of life from K2-14b were no longer confined to the scientific elite. They had found their way into the public consciousness, forcing everyone, scientists, philosophers, politicians, and ordinary people alike, to reckon with a question that had haunted humanity for millennia. Are we truly alone in the universe? The realization that life existed on another world caused an immediate stir. Governments, media, and universities scrambled to process the full ramifications of the discovery. The world had to confront the possibility that life, not just on K2-18b, but in countless other places across the galaxy, was not an anomaly. It was a common occurrence. The first wave of response came from the field of astrobiology. Researchers began to revisit old theories, recalibrating the search for life beyond Earth. As the data from Webb poured in, scientists started to recognize patterns that could be replicated across other star systems. Suddenly, the vastness of the universe no longer felt empty. It felt teeming with potential life waiting to be discovered. K2-18b had unlocked the door to a new chapter in our understanding of the cosmos, one where life's signature could be detected not just by the rarity of Earth-like conditions, but by the universality of chemical processes that sustain it. Yet, as much as K2-18b's discovery sparked excitement, it also raised profound ethical, philosophical, and existential questions. Humanity had long regarded itself as the pinnacle of life in the universe. To learn that life could thrive on a planet so different from Earth challenged not just our place in the cosmos, but the very notion of what life is and what it means to be human. This realization hit particularly hard for scientists like Medusan. The journey to uncovering the truth about K2-18b had been one of immense excitement, but it also carried a deep sense of responsibility. As humanity stared into the face of this cosmic discovery, questions began to arise. If life existed elsewhere, what did it mean for the future of our species? Would we reach out to these distant worlds, or would we leave them undisturbed? What right did humanity have to claim the universe as its own? For some, the discovery was a moment of triumph. It was proof that life was not rare, that the principles that allowed life to thrive on Earth were universally applicable. To others, it was a reminder of the fragility of life itself. The quiet beauty of K2-18b, where evolution unfolded slowly and steadily under a dim red sun, was a stark contrast to the chaotic, turbulent history of our own planet. For the first time, humanity had to reckon with the realization that we were not alone, and that we might not be as unique as we once believed. As the days passed, Medusan began to feel the weight of this realization more and more. The data coming from Webb, though exhilarating, only deepened the mystery. It wasn't just the discovery of life on K2-18b that had shifted everything. It was the knowledge that there were likely countless other planets in the galaxy where life, in one form or another, was thriving. The Milky Way alone, with its estimated 100 billion stars, was a vast ocean of possibilities. But what kind of life existed out there? What did it look like? How did it survive? At this point, the scope of the discovery began to shift from the discovery of a single world to the understanding of an entire class of planets, those that orbit red dwarf stars like K2-18b. Red dwarfs were once thought to be poor candidates for supporting life. Their faint dim light and the close proximity of their planets to the stars were seen as obstacles. But K2-18b had turned those assumptions on their head. The quiet, steady rhythm of a red dwarf star, rather than being a hindrance, had given K2-18b the stability and time it needed to allow life to flourish. And If K2-18b had this stability, how many other worlds could share this same fate? The question that now consumed Medusan was not whether life existed elsewhere, but how far this cosmic network stretched. What would the future of exploration look like if humanity were to extend its reach beyond the stars and discover not just one K2-18b, but a multitude of thriving worlds, each with its own distinct form of life? In the midst of this exploration, one of the most astonishing questions to emerge was whether or not humanity was ready to meet these new life forms. Earth had barely begun to address the complexity of its own environment, much less face the reality of interstellar life. If contact were to be made with life on another planet, what kind of message would we send? Would we approach these distant worlds with curiosity and respect, or would we impose our own views and ways of life upon them? This question of first contact, which had been discussed in science fiction for years, had suddenly become an imminent reality. It was no longer just a philosophical debate. It was a pressing issue. And humanity, as a species, had to figure out how to navigate it. Would we engage with other civilizations? Would we attempt to learn from them? Or would we leave them undisturbed, preserving the integrity of their ecosystems? The question also reached into the realm of ethics. How would we treat these newfound life forms? If we discovered that they were intelligent, would we attempt to communicate with them? What if they were not intelligent, but still possessed the ability to affect the course of their ecosystems? Would we have the ethical responsibility to protect these alien worlds, or would we regard them as open territory to be explored and exploited? These were questions that no one had anticipated answering so soon. K2-18b had forced humanity to look at the stars not just as an endless expanse to be conquered, but as a network of living worlds that shared a common rhythm. It was a humbling realization, a reminder that life in the universe is not defined by the earthly experience, but by a much broader set of principles that extend far beyond our own understanding. As the weeks wore on and more data arrived, Medusan and his team began to reach a new conclusion. The discovery of K2-18b was not just a scientific breakthrough, it was a turning point in human history. It marked the end of one chapter and the beginning of another, a chapter in which humanity was no longer a solitary species in a cold and silent universe, but a part of a living, breathing cosmos, one where life was not an accident, but a constant presence. The implications were staggering. The discovery of life on K2-18b meant that humanity was not alone, but it also meant that the search for life was no longer about finding other Earths. It was about recognizing the vast array of possibilities that life could take, shaped by the unique conditions of each world. As the realization of K2-18b's significance spread across the scientific community, the focus of the discovery began to shift from pure exploration to more profound, pressing concerns. The excitement over finding life on another world soon gave way to a deeper, more complex conversation. What did this discovery mean for humanity's future? What was our place in a universe that was far more populated than we ever imagined? And, most importantly, what responsibilities did we now face as a species who had just learned they were not alone? For Medusan and his team, the euphoria of discovery had quickly evolved into a new, more urgent mission: to understand how this newfound knowledge should shape humanity's next steps. The science had been clear. K2-18b harbored life, thriving beneath its red dwarf star, but the implications reached far beyond the chemistry of distant planets. The discovery was a clarion call, urging humanity to reconsider its very approach to life, the cosmos, and its place within both. The ethical questions surrounding K2-18b's discovery were immediate and profound. While the initial thrill of the find had been shared by the scientific community, a quieter, more somber reflection began to settle in. Scientists, philosophers, ethicists, and policymakers around the world began asking a simple yet dawning question: what do we do now? Should humanity reach out to the life on K2-18b, eager to make contact and establish communication, Or would that be an imposition on a world that had evolved in isolation for billions of years? Would our presence disrupt the delicate balance that allowed life to thrive on K2-18b, or would we bring with us knowledge that could help that world continue its evolutionary journey? These questions were not hypothetical. In the wake of the discovery, international leaders convened to discuss the next steps, not only in terms of space exploration, but in terms of interstellar ethics. The governing principles that had guided humanity's exploration of space, treating other worlds as uninhabited frontiers to be explored and studied, were suddenly thrown into question. The discovery of K2-18b was a direct challenge to the assumptions that had long governed our approach to the cosmos. It demanded that humanity reframe its understanding of what it meant to be stewards of the universe. The situation was complicated by the reality that we had only just begun to understand the biology of K2-18b. We had detected the chemical signatures of life, dimethyl sulfide, methane, and carbon dioxide, proving that life thrived there. But we had not yet made contact with any form of that life. We had no idea what it looked like, how it interacted with its environment, or whether it could even comprehend the existence of intelligent life from another world. Yet the very act of discovery, of unveiling the truth about K2-18b, had irrevocably changed the landscape of human thought. The debate was no longer about whether life existed elsewhere in the universe. We had the proof. The question was now one of morality and responsibility. The interplanetary dilemma. At a United Nations session, representatives from all over the world discussed the future of space exploration and the ethical guidelines that should govern it. The discovery of life on K2-18b prompted a shift in international space law, which had been formulated in the 1960s during the early days of space exploration. The Outer Space Treaty of 1967, which served as the foundation of modern space law, was written long before we had the capability to detect distant life. The treaty emphasized that space exploration should be conducted for the benefit of all nations and that activities on other celestial bodies should avoid harmful contamination. But what constituted harmful contamination in a galaxy teeming with life? Could the presence of humanity itself be an imposition on these alien ecosystems, even if we never physically stepped foot on K2-18b? And if we were to make contact, what safeguards could ensure that we did not introduce invasive species or unwittingly disrupt the balance of an alien world? The most difficult question was one of intervention. Would humanity, in its eagerness to explore, try to terraform or alter environments like K2-18b? What if we began to mine resources from these planets, extracting materials that could change their fragile ecosystems forever? Such questions presented profound ethical dilemmas that had never been fully addressed before, as humanity had never been forced to consider the possibility of sharing the universe with other life forms. For centuries, space exploration had been framed as a mission of human progress, expansion, and survival. The race to conquer new frontiers, whether it be the Moon, Mars, or distant exoplanets, had always been about humanity's desire to stretch the boundaries of its existence. But now, with K2-18b, that view seemed outdated. What if, instead of seeking to conquer, humanity's role was to act as guardians and stewards of the cosmos? The question of communication. Perhaps the most pressing issue was the potential for communication with the life forms of K2-18b. If the planet's life forms were anything like those on Earth, then communication could be possible. But how would we even begin to communicate with beings from another world, whose chemistry, biology, and sensory perceptions might be entirely foreign to ours? Would we rely on sound, light, or other signals? Could we establish a meaningful exchange, or would we be forever separated by the vast distance between our worlds? One of the most critical aspects of any potential communication would be understanding the biology and chemistry of the life on K2-18b. Medusan and his team knew that if they were to continue studying the planet, they would need to collect more data. But what could they learn from this world without causing harm? Could their research methods be adapted to ensure that they didn't disturb the planet's ecosystem or inadvertently introduce contamination? As humanity faced these questions, the scientific community began to forge a path forward that combined exploration with humility. Rather than rushing headlong into colonization or exploitation, the new generation of space explorers, scientists, and ethicists were committed to learning first, learning about K2-18b and other potential habitable worlds, while respecting the autonomy of the ecosystems they encountered. A new age of exploration. The discovery of life on K2-18b marked the beginning of a new era in space exploration. For the first time, humanity was no longer just an isolated species in a vast universe. We were participants in a cosmic network, connected to worlds beyond our own by the fundamental principles of biology and chemistry. K2-18b had shown us that life was not a rare, fragile phenomenon, but a process that could unfold in countless forms, given the right conditions. But as the excitement of discovery gave way to reflection, humanity began to realize that this new age of exploration would require something far more profound than just scientific knowledge. It would require wisdom, patience, and ethical foresight. The same qualities that had allowed life to evolve on K2-18b under the steady light of a red dwarf star would now need to be applied to humanity's journey into the stars. The discovery of life on K2-18b was no longer just a scientific breakthrough. It had become a global event that transcended national borders, academic fields, and even the political and economic interests of Earth's nations. As the news spread like wildfire, governments, corporations, universities, and media outlets found themselves at the center of a new age of cosmic discovery, one that reshaped humanity's relationship with the universe and with one another. The first weeks after the announcement were marked by an overwhelming wave of reactions. The scientific community was abuzz with excitement, but this was not a moment of triumphalism. It was a moment of collective reflection. The scale of the discovery had prompted an urgent question. How do we, as a species, navigate our newfound knowledge that we are not alone in the universe? For the first time, humanity was confronted not just with the possibility of other life, but with the reality that life beyond Earth was thriving in places vastly different from our home. K2-18b's thriving ecosystem, with its vast oceans beneath a hydrogen-rich atmosphere, its red sun that glowed softly in the vastness of space, was a world that required a new way of thinking, one that moved beyond the human-centric view that had long governed our exploration of the cosmos. The initial response was mixed. Some factions celebrated the discovery as the beginning of a new golden age of space exploration. Others, however, cautioned against acting hastily, urging governments and international bodies to consider the ethical implications of interacting with these distant, potentially fragile ecosystems. There was a growing sense of responsibility among scientists and ethicists alike, a realization that humanity had not just discovered something extraordinary, but had also unlocked the potential to irrevocably change the future of other worlds. As the discovery spread across the globe, the scientific community recognized that this was not merely about the search for life. It was a call for humanity to evolve its perspective on exploration, stewardship, and engagement with the cosmos. For too long, space exploration had been guided by a mentality of ownership and conquest. Governments and corporations aiming to expand humanity's influence across the solar system, colonizing new worlds. But now, the discovery of K2-18b's vibrant and balanced ecosystem posed a stark challenge to that mentality. The question wasn't just about how humanity could explore the stars, but about how we should do so without harming what we found. The global response to K2-18b's discovery led to the realization that space law, which had been crafted in the 1960s when the notion of finding life beyond Earth was still speculative, needed to be revisited. The Outer Space Treaty, which governed the exploration and use of outer space, had been written with the understanding that celestial bodies were uninhabited and there was no immediate threat of encountering life. It emphasized peaceful use and the prevention of territorial claims, but it did not account for the ethical complexities of discovering alien ecosystems. With the discovery of life on K2-18b, the treaty was suddenly inadequate. The international space community quickly realized that the next steps in space exploration would require a new legal framework, one that not only governed exploration, but also the protection of alien life forms and ecosystems. The Extraterrestrial Life Protection Protocol was introduced as an extension of the existing Outer Space Treaty. This new protocol mandated that all nations and private companies involved in space exploration adopt strict measures to ensure that any engagement with life-supporting planets would be conducted with extreme caution and that their ecosystems would be preserved. For many nations, the ethical implications of exploring and interacting with alien ecosystems became the focus of debate. How could humanity ensure that it did not make the same mistakes it had made on Earth? How could we avoid the temptation to exploit and deplete new worlds as we had so often done with our own planet? The realization that K2-18b was a living world had forced humanity to confront the environmental consequences of its actions in a new context. The galaxy, it seemed, was not a void to be filled with human ambition, but a vast network of worlds, each with its own natural harmony, each deserving of respect. At the same time, private companies which had rapidly gained a foothold in the realm of space exploration found themselves caught up in these new discussions. With the capabilities of companies like SpaceX and Blue Origin advancing rapidly, the future of space exploration had shifted from government agencies to corporate entities. The growing role of private corporations in space exploration added a layer of complexity to the conversation. Governments now faced the challenge of ensuring that these corporations did not view distant planets, such as K2-18b, as mere resources to be exploited. Rather than allowing corporate interests to dominate, the global community recognized the need for regulations that would balance exploration with conservation. As more data from K2-18b continued to come in, it became clear that the planet's ecosystem, though thriving, was also fragile. Its thick hydrogen-rich atmosphere, which had allowed life to flourish under a steady red dwarf star, was the product of billions of years of delicate balance. The realization that this balance could easily be disrupted by human interference led to the idea of a new age of exploration, one where discovery and scientific advancement would go hand in hand with deep respect for the environments we encountered. The galaxy was not a frontier to be tamed, but a living system to be studied and protected. The ethical questions surrounding K2-18b were not just theoretical. They had real-world implications for how humanity would approach the future of space exploration. If we discovered other planets that also harbored life, would we attempt to colonize them, or would we instead protect them, ensuring that we did not repeat the mistakes of history? Could humanity learn to coexist with the life it discovered, not just as explorers, but as guardians of the cosmos? As Medusan and his team continued to analyze the data from K2-18b, they began to understand that their work was part of something much larger than just the study of an alien world. They were writing the first chapters of a new era in which humanity would learn to understand its place in the cosmos, not as conquerors, but as stewards of life itself. This shift in perspective was both humbling and empowering. For the first time, humanity was asked to see itself not as the center of the universe, but as a small, interconnected part of a vast and diverse cosmic system. The ethical questions raised by K2-18b's discovery were not just for scientists or world leaders to answer. They were questions that the entire global community had to grapple with. As space exploration moved forward, it would no longer be just about reaching new frontiers. It would be about how humanity would choose to engage with the life it discovered in the stars. Would we be driven by curiosity and a desire for knowledge? Or would we be guided by a sense of responsibility and respect for the unknown worlds we encountered? The discovery of K2-18b was a reminder that space exploration was no longer about finding new worlds to dominate, but about recognizing the deep, unspoken connections that linked all life in the universe. The new age of exploration was not just about charting new territory. It was about understanding and protecting the living systems that existed beyond Earth, ensuring that they could thrive for millennia to come. The discovery of life on K2-18b was no longer just a scientific breakthrough. It had become a global event that transcended national borders, academic fields, and even the political and economic interests of Earth's nations. As the news spread like wildfire, governments, corporations, universities, and media outlets found themselves at the center of a new age of cosmic discovery, one that reshaped humanity's relationship with the universe and with one another. The first weeks after the announcement were marked by an overwhelming wave of reactions. The scientific community was abuzz with excitement, but this was not a moment of triumphalism. It was a moment of collective reflection. The scale of the discovery had prompted an urgent question. How do we, as a species, navigate our newfound knowledge that we are not alone in the universe? For the first time, humanity was confronted not just with the possibility of other life, but with the reality that life beyond Earth was thriving in places vastly different from our home. K2-18b's thriving ecosystem, with its vast oceans beneath a hydrogen-rich atmosphere, its red sun that glowed softly in the vastness of space, was a world that required a new way of thinking, one that moved beyond the human-centric view that had long governed our exploration of the cosmos. The initial response was mixed. Some factions celebrated the discovery as the beginning of a new golden age of space exploration. Others, however, cautioned against acting hastily, urging governments and international bodies to consider the ethical implications of interacting with these distant, potentially fragile ecosystems. There was a growing sense of responsibility among scientists and ethicists alike, a realization that humanity had not just discovered something extraordinary, but had also unlocked the potential to irrevocably change the future of other worlds. As the discovery spread across the globe, the scientific community recognized that this was not merely about the search for life. It was a call for humanity to evolve its perspective on exploration, stewardship, and engagement with the cosmos. For too long, space exploration had been guided by a mentality of ownership and conquest, governments and corporations aiming to expand humanity's influence across the solar system, colonizing new worlds. But now, the discovery of K2-18b's vibrant and balanced ecosystem posed a stark challenge to that mentality. The question wasn't just about how humanity could explore the stars, but about how we should do so without harming what we found. The global response to K2-18b's discovery led to the realization that space law, which had been crafted in the 1960s when the notion of finding life beyond Earth was still speculative, needed to be revisited. The Outer Space Treaty, which governed the exploration and use of outer space, had been written with the understanding that celestial bodies were uninhabited and there was no immediate threat of encountering life. It emphasized peaceful use and the prevention of territorial claims, but it did not account for the ethical complexities of discovering alien ecosystems. With the discovery of life on K2-18b, the treaty was suddenly inadequate. The international space community quickly realized that the next steps in space exploration would require a new legal framework, one that not only governed exploration, but also the protection of alien life forms and ecosystems. The Extraterrestrial Life Protection Protocol was introduced as an extension of the existing Outer Space Treaty. This new protocol mandated that all nations and private companies involved in space exploration adopt strict measures to ensure that any engagement with life-supporting planets would be conducted with extreme caution and that their ecosystems would be preserved. For many nations, the ethical implications of exploring and interacting with alien ecosystems became the focus of debate. How could humanity ensure that it did not make the same mistakes it had made on Earth? How could we avoid the temptation to exploit and deplete new worlds, as we had so often done with our own planet? The realization that K218b was a living world had forced humanity to confront the environmental consequences of its actions in a new context. The galaxy, it seemed, was not a void to be filled with human ambition, but a vast network of worlds, each with its own natural harmony, each deserving of respect. At the same time, private companies, which had rapidly gained a foothold in the realm of space exploration, found themselves caught up in these new discussions. With the capabilities of companies like SpaceX and Blue Origin advancing rapidly, the future of space exploration had shifted from government agencies to corporate entities. The growing role of private corporations in space exploration added a layer of complexity to the conversation. Governments now faced the challenge of ensuring that these corporations did not view distant planets, such as K2 and 18b, as mere resources to be exploited. Rather than allowing corporate interests to dominate, the global community recognized the need for regulations that would balance exploration with conservation. As more data from K218b continued to come in, it became clear that the planet's ecosystem, though thriving, was also fragile. Its thick, hydrogen-rich atmosphere, which had allowed life to flourish under a steady red dwarf star, was the product of billions of years of delicate balance. The realization that this balance could easily be disrupted by human interference led to the idea of a new age of exploration, one where discovery and scientific advancement would go hand in hand with deep respect for the environments we encountered. The galaxy was not a frontier to be tamed, but a living system to be studied and protected. The ethical questions surrounding K218b were not just theoretical. They had real-world implications for how humanity would approach the future of space exploration. If we discovered other planets that also harbored life, would we attempt to colonize them, or would we instead protect them, ensuring that we did not repeat the mistakes of history? Could humanity learn to coexist with the life it discovered, not just as explorers, but as guardians of the cosmos? As Medusan and his team continued to analyze the data from K218b, they began to understand that their work was part of something much larger than just the study of an alien world. They were writing the first chapters of a new era in which humanity would learn to understand its place in the cosmos, not as conquerors, but as stewards of life itself. This shift in perspective was both humbling and empowering. For the first time, humanity was asked to see itself not as the center of the universe, but as a small, interconnected part of a vast and diverse cosmic system. The ethical questions raised by K218b's discovery were not just for scientists or world leaders to answer. They were questions that the entire global community had to grapple with. As space exploration moved forward, it would no longer be just about reaching new frontiers. It would be about how humanity would choose to engage with the life it discovered in the stars. Would we be driven by curiosity and a desire for knowledge, or would we be guided by a sense of responsibility and respect for the unknown worlds we encountered? The discovery of K218b was a reminder that space exploration was no longer about finding new worlds to dominate, but about recognizing the deep unspoken connections that linked all life in the universe. The new age of exploration was not just about charting new territory. It was about understanding and protecting the living systems that existed beyond Earth, ensuring that they could thrive for millennia to come. End of Part 5. Would you like me to continue with Part 6 and delve into the scientific advancements that are shaping the future of interstellar exploration? Give me Part 6. Part 6, the advancements and challenges ahead. As the global conversation surrounding K218b's discovery continued to unfold, humanity stood on the precipice of a new era, one in which space exploration was no longer just about scientific curiosity, but about understanding the very fabric of life across the cosmos. The implications of finding a living world so far beyond Earth had sparked a renewed sense of purpose in the scientific community. It was not just about proving that life existed elsewhere. It was about learning how to engage with the universe in a way that was ethical, sustainable, and respectful of the delicate balance that allowed life to thrive in the first place. To truly understand K218b and other potential alien biospheres, humanity would need to advance its technologies and methodologies beyond what was previously thought possible. The data coming from the James Webb Space Telescope was only the beginning. For Medusan and his team, as well as for the growing global network of scientists, the work ahead was vast and complex. They would have to find new ways to analyze alien atmospheres, detect subtle changes in chemical patterns, and map the ecosystems of distant worlds with an unprecedented level of precision. One of the key challenges was developing the technology to directly explore K2-18b's atmosphere. While Webb's instruments had given humanity its first glimpse into the chemistry of an alien world, those insights were still distant, interpreted through light years of space. The next phase of exploration would require humanity to send probes and possibly even crewed missions to study the planet in situ. But that task came with enormous technical hurdles. K2-18b's thick, hydrogen-rich atmosphere was unlike anything Earth-based instruments had ever encountered. The sheer depth of the atmosphere and the dense clouds of vapor posed significant challenges for traditional space probes. Unlike Mars with its relatively thin atmosphere or Venus with its acid-rich clouds, K218b presented a unique set of environmental conditions. Its hydrogen-rich air was both dense and chemically reactive, making it difficult to analyze from a distance, let alone land on its surface or send a probe deep into its oceans. The first technological hurdle would be sending probes that could withstand the immense pressures of the planet's lower atmosphere and reach the depths of its oceans. The pressure in K2-18b's waters was expected to be much greater than the deepest part of Earth's oceans. Yet, as humanity had learned from exploring our own ocean depths, extreme pressure could be both an obstacle and an opportunity. At these depths, the chemistry of life on K2-18b could be far more complex and exotic than anything seen on Earth. Could life there use the immense pressure to catalyze chemical reactions that were impossible elsewhere? Could the organisms on K218b have evolved to thrive under conditions that would crush anything from Earth? To overcome these challenges, space agencies and private companies would need to develop new materials and technologies. Scientists began to look to deep-sea exploration as a guide, drawing parallels between the oceanic trenches of Earth and the deep pressurized oceans of K2-18b. Technologies designed to withstand the crushing pressures of Earth's deep oceans could provide the foundation for probes capable of surviving the harsh conditions of alien worlds. Advanced carbon-based materials, self-healing polymers, and reinforced metals could be the keys to building instruments capable of surviving the depths of K218b's alien seas. At the same time, advancements in artificial intelligence, AI, were rapidly transforming space exploration. AI systems already used to analyze massive datasets from telescopes and space probes would be critical in interpreting the complex signals coming from distant planets. As K218b's signals, its chemical signatures, were gathered in greater detail, AI algorithms would help scientists recognize patterns that might otherwise be missed. Machine learning models, trained to identify potential biosignatures, would enable real-time analysis of alien environments, dramatically increasing the speed and accuracy of exploration. But AI was not just about data analysis. As space exploration advanced, AI would play a more direct role in space missions. Autonomous robots, guided by sophisticated AI, could explore the surface of K2-18b, navigate its oceans, and even interact with the environment in ways humans could not. These robots, designed to withstand the extreme conditions of K2-18b's atmosphere and oceans, could be our first emissaries to alien worlds. They could be programmed to gather information, perform experiments, and adapt to the ever-changing conditions of the alien environment. AI-driven systems were also being developed to support deep space navigation. As humanity moved beyond our solar system, the challenges of interstellar travel would require autonomous systems capable of adjusting to the unpredictable nature of space. The vast distances between stars, the unpredictable behavior of deep space objects, and the need for precision in travel made it clear that AI would be indispensable in guiding missions to distant exoplanets. Yet, these technological advances came with their own set of risks and challenges. The further humanity ventured into space, the greater the risks of contamination, both for Earth and for the worlds we explored. The need for planetary protection protocols had never been more urgent. As we developed the technology to explore K2-18b and other distant worlds, we also needed to ensure that our missions did not inadvertently introduce Earth-based organisms that could disrupt the delicate ecosystems of these alien planets. Planetary protection was a field that had gained new importance in light of the discovery of life on K2-18b. The protocols established by international space agencies, which had once focused solely on preventing the contamination of Earth from extraterrestrial pathogens, now had to be updated to include the protection of alien biospheres. The idea of back contamination, or the risk of bringing alien life back to Earth, was no longer the only concern. The real challenge was preventing forward contamination, ensuring that human missions did not inadvertently alter the ecosystems of distant planets like K2-18b. For the first time, planetary protection protocols were being expanded to encompass the concept of cosmic stewardship, a responsibility to preserve the life and environments we encountered in space. The role of artificial intelligence was not just limited to exploration and data analysis. It would also play a pivotal role in managing the ethical dilemmas that arose from these discoveries. With the global community still grappling with the implications of K2-18b's lifeforms, AI systems could be used to simulate various scenarios, exploring potential consequences of contact or interference with alien ecosystems. These AI-driven simulations could help policymakers make decisions that balanced scientific curiosity with ethical responsibility. The discovery of life on K2-18b had ignited a profound shift in humanity's ambitions and perceptions of space exploration. No longer was the question simply whether life could exist elsewhere in the universe. It was about how humanity would navigate its place within a cosmos teeming with potential life. K2-18b had shown that life could thrive in environments vastly different from Earth, challenging every preconceived notion about what made a world habitable. But beyond the scientific and philosophical implications, one question remained pressing. How would humanity take the next step in its exploration of these distant worlds? For decades, space exploration had been limited to the confines of our solar system, with missions to Mars, Jupiter, and beyond. While these missions had expanded our understanding of our cosmic neighborhood, the vastness of space still seemed an insurmountable barrier. But K2-18b's discovery changed that. Suddenly, the universe did not seem so empty. It was alive with possibility. The immediate response from space agencies was to ramp up efforts for interstellar exploration, focusing on technologies that could carry humanity to the stars. The discovery of life beyond Earth meant that space exploration was no longer just about scientific curiosity. It was about securing humanity's place in a broader cosmic ecosystem. But the challenge was immense. At present, humanity's spacefaring capabilities were limited to the reaches of our solar system. We had no technology capable of reaching K2-18b in a human lifetime, much less exploring a network of alien worlds. Even if we could send a spacecraft toward K2-18b, the journey would take centuries, decades beyond the span of a human life. The gap between our current abilities and the long-term dream of interstellar travel felt more pronounced than ever. This challenge, however, was far from insurmountable. Over the past decade, advances in propulsion technology had begun to change the conversation. While chemical rockets had propelled humanity into space for decades, they were slow and inefficient when it came to interstellar travel. To reach K2-18b, let alone explore other distant stars, we would need propulsion systems that could achieve a significant fraction of the speed of light, systems capable of shortening a journey that would otherwise span centuries. Scientists and engineers had begun exploring several promising ideas. One of the most exciting developments was the concept of nuclear fusion propulsion. Fusion, the process that powers the stars, has long been theorized as a potential energy source for space travel. The concept behind fusion propulsion is simple: harness the power of the stars themselves to propel a spacecraft. With fusion engines, it would be possible to achieve much higher speeds than chemical rockets, potentially enabling interstellar travel within a human lifetime. NASA and private companies like SpaceX were already working on early-stage fusion propulsion experiments, with the goal of testing these technologies within the next few decades. If successful, this would mark a monumental breakthrough in our ability to travel beyond our solar system, turning the dream of interstellar exploration into a tangible goal. Another promising avenue of research was the Breakthrough Starshot initiative, which proposed sending small, lightweight probes to the stars using powerful lasers to accelerate them to a significant fraction of the speed of light. These probes, equipped with cameras and sensors, could be sent on missions to distant exoplanets like K218b, gathering crucial data without the need for slow-moving spacecraft. While the technology for such missions was still in its infancy, it was a powerful reminder that the barriers to interstellar exploration were not fixed. They were merely challenges waiting to be solved. As the technological landscape evolved, one thing was clear: humanity was no longer limited to the confines of our solar system. The discovery of life on K218b had opened a new frontier, one that would require not just technological advancements, but a shift in human imagination. Interstellar travel was no longer the realm of science fiction. It was becoming a concrete, if distant, goal. The road ahead: technological innovation and global cooperation. The journey to K218b and to other distant exoplanets was no longer a question of if, but when. However, this new age of exploration would require a level of global cooperation and technological innovation that had never before been seen in human history. As the world's space agencies ramped up their efforts to make interstellar travel a reality, they were not doing so in isolation. The global nature of the discovery of life on K218b had fostered unprecedented cooperation between nations and private industries. From the United States and Europe to China and Russia, space agencies were working together to share data, resources, and expertise. It was a recognition that the future of space exploration was too vast, too complex to be pursued by any single nation. Instead, the world's spacefaring nations had to come together, pooling their knowledge and capabilities to chart a course for the stars. The role of private industry was also becoming more central to this global effort. The rise of companies like SpaceX, Blue Origin, and others had introduced an entrepreneurial spirit into space exploration, pushing the boundaries of what was possible. These companies, with their ambitious plans for space tourism, lunar bases, and even Mars colonization, were leading the charge in developing the technologies that could make interstellar travel a reality. Their innovative approaches and willingness to take risks were driving the technological advancements that were vital to humanity's progress. But the road ahead was not without its challenges. Beyond the technical and logistical hurdles of interstellar travel, there were profound ethical considerations. If humanity were to explore and eventually colonize other worlds, what responsibilities would we have to those ecosystems? How would we ensure that we did not repeat the mistakes of the past, exploiting resources and causing harm to the environments we encountered? These questions would need to be addressed not just by scientists and engineers, but by ethicists, policymakers, and the global community as a whole. As Medusan and his team continued their work on K218b, they realized that they were not just pioneers of a new era of exploration, they were stewards of a new responsibility. The discoveries being made were not just about gathering knowledge. They were about preparing humanity for a future in which we were no longer alone in the universe. A future where we shared the stars with life forms on distant worlds and where we had to learn how to coexist with them rather than conquer them. In the coming decades, humanity would have to face these questions head-on. As we develop the technology to travel to distant stars and explore alien worlds, we would also need to develop the wisdom to know how to act. The discovery of life on K2-18b was not just a scientific achievement, it was a reminder that our place in the cosmos was not one of dominance, but of interconnectedness. The discovery of life on K2-18b, far from being just a milestone in the history of space exploration, had sparked a profound shift in human consciousness. It was not just a question of finding life beyond Earth, it was a question of understanding humanity's place in the cosmos. For millennia, humans had looked up at the stars, imagining ourselves as the center of creation, a unique species in a vast, empty universe. But now, the truth had become undeniable. Life was not an anomaly. It was a fundamental principle, a cosmic constant. And we were not alone. As the years passed and humanity continued to explore the implications of K2-18b's discovery, a deep reflection began to take root in our collective psyche. The universe had revealed itself as a living, breathing entity, filled with worlds, teeming with life, each shaped by the same forces that had shaped Earth. This revelation changed the way we thought about ourselves, not just as individuals, but as a species. The most immediate impact of K2-18b's discovery was felt in philosophy. For centuries, humanity had asked whether life existed elsewhere in the universe. Now that the answer was clear, the question shifted. No longer were we wondering if life was out there. We were now faced with the reality of what this discovery meant for the very nature of existence. The answers we had once found in religion, mythology, and science fiction now had a new context. We were part of a greater cosmic community, one that extended far beyond the boundaries of Earth. This realization had a profound impact on the way humans viewed their relationship with the universe. In the past, we had seen ourselves as a species separate from the natural world, as masters of the Earth and its resources. But as we gazed into the depths of space, we were reminded of our own fragility. The discovery of life on K2-18b showed us that life was not rare or miraculous. It was a recurring theme in the universe, shaped by the same laws of chemistry and physics that governed our own existence. We were not an exception. We were an expression of the universe's inherent creativity. This realization forced humanity to confront the ethical questions of our future in space. If life was everywhere, how should we interact with it? Would we treat these new worlds with the respect they deserved, or would we impose our own desires, ambitions, and ideologies on them? The lessons learned from the discovery of K2-18b were not just about how we explored space. They were about how we would live on Earth, how we would relate to the world around us, and how we would ensure the survival of life, not just on our planet, but across the cosmos. In this new age of exploration, humanity was called upon to act with responsibility, humility, and wisdom. The discovery of life on K2-18b had shown us that the universe was a living, interconnected system, one where the balance of life was delicate and precious. We could no longer afford to view space as a vast, empty void to be conquered. Instead, we had to learn to see it as a living ecosystem, one that we were a part of, not separate from. As humanity turned its gaze outward, there was also an inward reflection that occurred. The implications of the discovery touched not only our understanding of the universe, but also our own sense of self. For centuries, humanity had defined itself in opposition to the natural world, conquering it, shaping it, and imposing our will upon it. But now, with the realization that we were not alone, humanity was faced with a choice. We could continue down the path of dominance and exploitation, or we could choose a new way, one that embraced cooperation, sustainability, and stewardship. This shift in perspective began to manifest in every facet of human society. New philosophies emerged that challenged traditional views of humanity's place in the world. The idea that humans were not at the center of the universe, but rather a part of a larger interconnected web of life, took root in political, environmental, and cultural movements around the globe. Environmentalism, which had long been about protecting Earth's ecosystems from human interference, now evolved into a broader movement to protect life across the cosmos. The idea of preserving life on K218b and other alien worlds became a guiding principle for space exploration, alongside the desire to understand and learn from those worlds. Politically, the discovery of life beyond Earth led to a new era of international cooperation. The challenge of exploring alien worlds, ensuring their preservation, and understanding their ecosystems became a global endeavor. Countries that had once competed for dominance in space began to work together toward a common goal, not to claim new territories, but to explore the unknown with respect, curiosity, and care. This spirit of cooperation extended beyond space agencies and governments. Private corporations, too, began to recognize the need for ethical guidelines in their pursuit of space exploration, with many stepping up to support efforts for planetary protection and environmental responsibility. The implications of K218b's discovery also reached into the realm of religion and spirituality. For many, the revelation that life existed beyond Earth challenged traditional religious teachings about humanity's unique place in the universe. But rather than causing division, this discovery sparked a deeper understanding of the divine. Many religious leaders embraced the idea that life, in all its forms, was a reflection of a greater, universal force, a force that transcended the boundaries of individual belief systems. This new perspective allowed for a more inclusive understanding of creation, one that saw the divine not as confined to a single planet, but as a force that permeated the entire universe, sustaining life wherever it could thrive. As the years passed, humanity's sense of purpose began to shift. No longer were we simply a species trying to survive in an indifferent universe. We were part of a larger cosmic narrative, one that stretched across light years and spanned countless worlds. The discovery of life on K218b was not the end of humanity's journey, but the beginning of a new chapter. A chapter in which we learn to see ourselves as participants in a cosmic ecosystem, not as conquerors, but as caretakers. The story of K218b, of life found on a distant world, was just one of many that humanity would uncover. As we continued to search the stars, we would find more answers, more worlds, and more signs of life. But with each new discovery, we would also be faced with the same fundamental question. How will we choose to engage with these new worlds? Will we act with wisdom and humility, or will we repeat the mistakes of the past? For now, the discovery of life on K218b serves as a reminder that life is not fragile, but persistent. It is the universe's most eloquent form of continuity. We are not an exception to the laws of nature, we are an expression of them. And as we continue to look outward into the cosmos, we will come to realize that the universe is not a cold, silent place. It is alive, teeming with life, and we are not alone. In the end, the discovery of K218b was not just a triumph of science. It was a triumph of humanity's enduring quest for understanding, connection, and ultimately, meaning. As we continue to explore the stars, we will do so not as solitary observers, but as participants in the shared rhythm of the cosmos. The discovery of life on K218b marks the beginning of a new era, a new age in which we will learn, grow, and discover not just new worlds, but a deeper understanding of our own place in the universe.